In our previous session, we learned that KVM transforms the Linux kernel into a Type 1 hypervisor, while QEMU creates the complete virtual hardware environment required by every virtual machine. But this raises an important question. If KVM provides hardware virtualization and QEMU creates the virtual machine, then who actually creates, starts, stops, and manages those virtual machines? The answer is Libvirt. Libvirt is not a hypervisor, and it does not emulate hardware like QEMU. Instead, it acts as a management layer that sits above virtualization technologies and provides a standardized way to control them. Rather than communicating directly with QEMU or KVM, enterprise platforms such as Proxmox VE, OpenStack, Cockpit, and Red Hat Virtualization use Libvirt as their management interface. This allows administrators to create virtual machines, modify hardware settings, perform live migrations, monitor resources, and automate infrastructure using a consistent set of APIs and management tools. Without Libvirt, every virtualization platform would need to communicate directly with individual hypervisors using different commands and different interfaces. Libvirt eliminates that complexity by providing a unified management framework for enterprise virtualization. Throughout this series, you will discover why Libvirt is often considered the brain behind KVM-based virtualization. In the next chapter, we will explore the Libvirt architecture and understand how the Libvirt service communicates with QEMU, KVM, and enterprise management platforms. In the previous chapter, we learned that Libvirt acts as the management layer between enterprise virtualization platforms and the underlying virtualization technologies. But how does Libvirt actually receive and process management requests? The answer is a background service called Libvirt. On Linux systems, Libvirt runs continuously as a daemon, waiting for management requests from applications such as Proxmox VE, Cockpit, OpenStack, Virsh, or other software using the Libvirt APIs. Whenever an administrator creates, starts, stops, restarts, pauses, or deletes a virtual machine, the request is not sent directly to QEMU or KVM. Instead, it is first received by the Libvirt service. Libvirt validates the request, checks the virtual machine configuration, verifies permissions, and determines which virtualization driver should handle the operation. If the request is valid, Libvirt communicates with QEMU to create or manage the virtual machine, while KVM provides the hardware-assisted virtualization capabilities inside the Linux kernel. This architecture allows administrators and management platforms to interact with a single, standardized interface instead of communicating separately with different hypervisors. In large enterprise environments, hundreds or even thousands of virtualization requests may be processed every day, making Libvirt one of the most important services in the entire virtualization stack. In the next chapter, we will explore how Libvirt APIs, Virsh, and management platforms communicate with Libvirt to control enterprise virtual machines. So far, we have learned that Libvirt is the service responsible for processing virtualization requests. But another important question remains. How do administrators and enterprise management platforms actually communicate with Libvirt? The answer lies in Libvirt APIs. Rather than communicating directly with QEMU or the Linux kernel, applications interact with Libvirt through a standardized programming interface. Whether the request comes from Proxmox VE, OpenStack, Cockpit, Red Hat Virtualization, the Virsh command line utility, or even a custom automation script, they all communicate with the same Libvirt API. Libvirt receives these requests, validates them, and forwards them to the appropriate virtualization driver. This standardized communication model eliminates the need for every management platform to understand the internal details of QEMU, KVM, Xen, or other supported hypervisors. Instead of learning different commands for different virtualization technologies, developers integrate with a single, consistent API. This approach makes enterprise virtualization easier to automate, simpler to maintain, and more reliable across different Linux environments. It also allows organizations to build their own management platforms without communicating directly with the hypervisor itself. In the next chapter, we will move from APIs to one of the most widely used administrative tools in enterprise Linux environments, Virsh, the command line interface built on top of Libvirt. So far, we have learned that Libvirt is the service responsible for processing virtualization requests. But another important question remains. How do administrators and enterprise management platforms actually communicate with Libvirt? The answer lies in Libvirt APIs. Rather than communicating directly with QEMU or the Linux kernel, applications interact with Libvirt through a standardized programming interface. Whether the request comes from Proxmox VE, OpenStack, Cockpit, Red Hat Virtualization, the Virsh command line utility, or even a custom automation script, they all communicate with the same Libvirt API. Libvirt receives these requests, validates them, and forwards them to the appropriate virtualization driver. This standardized communication model eliminates the need for every management platform to understand the internal details of QEMU, KVM, Xen, or other supported hypervisors. Instead of learning different commands for different virtualization technologies, developers integrate with a single, consistent API. This approach makes enterprise virtualization easier to automate, simpler to maintain, and more reliable across different Linux environments. It also allows organizations to build their own management platforms without communicating directly with the hypervisor itself. In the next chapter, we will move from APIs to one of the most widely used administrative tools in enterprise Linux environments. Throughout this series, we explored the complete role of Libvirt in modern Linux virtualization environments. We started by understanding that Libvirt is not a hypervisor itself. Instead, it acts as a management layer that connects enterprise tools with virtualization technologies such as KVM and QEMU. Behind every management request, there is a complete workflow. Applications and platforms communicate through Libvirt APIs, requests are processed by the Libvirt service, and then forwarded to the appropriate virtualization drivers. Tools like Virsh provide administrators with direct command line control, while enterprise platforms such as Proxmox VE, OpenStack, and other management solutions use the same standardized communication architecture. At the lower level, QEMU creates the virtual hardware environment, while KVM provides hardware-assisted virtualization capabilities through the Linux kernel. This layered design is what makes Linux virtualization flexible, scalable, and suitable for enterprise workloads. Instead of every management platform directly controlling hardware or individual hypervisor components, Libvirt provides a consistent framework that simplifies administration and automation. From small virtualization deployments to large cloud infrastructures, this architecture has become a fundamental building block of modern data centers. In the next part of our virtualization journey, we will explore another critical component of this ecosystem and understand how virtual machines are created, configured, and optimized in enterprise environments.